Have you ever wondered how to make a unit move smoothly in a strategy game? Or how game developers create realistic ballet trajectories in a first-person shooters? And what about those dynamic camera angles in cutscenes? Or how AI characters follow a perfect path without glitching? In this video, we are breaking down parametric line equations and how they are a key for these game mechanics. We'll explore how they are used to control movement, simulate physics, handle raycasting, and much more. So let's dive in. In the past video, we talked about the line defined via slope-intercept form. The y is equal to mx plus b. You can check it here if you want to refresh your memory. In this form, you have the y element of a point defined using x element of a point. And of course you need to have y-intercept and slope. Unfortunately, this is not a perfect form. In the further video, we are going to talk about rendering, and you will see how things changes if the slope of the line is bigger than 45 degrees. Obvious issue right now is that it's defined only using x and y. What if we want to work with lines in higher dimension? We need z. X and y are coordinates on Cartesian plane, and that's about it really. But we can do something different. We can imagine parameter t, and the parameter t is going to control where are we on our line. In the most natural example, the t is abbreviation of time, and its values might be whatever between 0 and 1. Let's start with an example. A parametric line equation describes a line using parameters. Instead of expressing y in terms of x, both x and y, or more dimensions, are expressed in terms of third variable, often called t. So let's say we want to define position of point r in some particular time t. For that, we need to have some r0. This is like the first point in a space which we are interested in, and some directional vector, v. So if we have a point and a vector, we have everything what we need to define a line. We added parameter t, so we can control how long the vector should really be. If you imagine 0, we are going to receive the position of the point r in the time 0, which is actually equal to r0. That seems to be alright. So this is a great example. You have a point and you have a vector. You can use this in FPS game to simulate shooting. If you want to make it even cooler, you can add things such as gravity. As you can see, it's basically the same thing. We are just going to accompany gravity, or gravitational acceleration to be precise. In a game dev scenario, it might happen that you have 2 points what you need to connect. Imagine that you have your unit standing somewhere and the user clicks somewhere using a mouse. So you have P0, you have P1. You can use the same equation. You shall just compute the vector v using these 2 points. Cool thing is that you have full control over the t parameter. If you want to use this for camera motion, for instance, you can easily add some easing. Easing out, easing in, to make your movement smooth or more sudden, exactly as you need. We can use the same equation if we want to use rays. If you imagine what the ray is or how it can be visualized, the ray is just a line, right? You have a point and you have a direction. Same thing. We can call it R to make it precise, and we can use this as a base for ray tracer. And actually we are going to program ray tracer in this channel, so don't forget to subscribe if you are interested. If we don't want to think about vectors, we can rewrite the equation to this form. P in time t is equal to 1 minus t times a plus t times b. Just to show you that it really doesn't matter, these are just letters. The concept is important. And that's actually the equation what I used in the previous video. If you know that t is something between 0 and 1, it's easy to see what's happening if you use these, let's say, maximum or minimum values. If you use 0, we have 1 minus 0, which is 1 times a, plus 0 times b. It means that our point on the line in time 0 is equal to point A, because 1 times A is A and 0 times B is nothing. In the same manner, if I choose 1, I have 1 minus 1, which is 0, times A, which erases the A, plus 1 times B. My point in time 1 is equal to B. It makes sense, right? So we are starting from 0, or A, and coming to B, which is 1. Very easy. And to illustrate how powerful this concept is, let's add third dimension. It is so easy as adding z elements to our points, and it works the same. We get talking about shots, about ray tracer, raycasting, about camera movement. And if you want to use this concept for unit movement, you can just compute x and y element of point P in some particular time using A and B, or P0 and P1, of some starting and ending point. And funny thing is that you can work with the t as you wish. You can start with 0 and write a cycle, plus 0.1, plus 0.1, plus 0.1, and make it linear. Or you can make the easing. You can use quadratic function. You can make your t 0.2, 0.4, 0.8, 1 to make the movement more interesting. You can do whatever you want. In the future video, we are going to apply this knowledge for an actual game. Thank you for watching. I really hope you learned something, and see you next time.